topic of my today's lecture is the finite population sampling technique to an infinite population. Actually, sampling we all know the term. We are all accustomed with the term sampling. It is nothing but a part of the population is needed to study, and we select this part of the population following some techniques. These techniques are altogether called sampling techniques. There are different types of sampling techniques. Based on probability, we have different types of probability sampling, and as well as we have some non-probability sampling. In this study, we have considered some probability-based sampling technique, and it is out of different types of probability sampling: simple random sampling, stratified sampling, systematic sampling, cluster sampling, and so on. In this paper, we have chosen systematic sampling. Actually, here our target is to select a sample in systematic manner from an infinite population. And next, we want to suggest a suitable estimator of population parameter and measure the precision of the suggested estimator through the calculation of risk. At the very first, we describe what systematic sampling is. Actually, systematic sampling is much more easier than simple random sampling. In systematic sampling, the population of size capital N units are divided into n groups of size k each, such that small k is equal to capital N by small n. Capital is nothing but the population size, and small n is the corresponding sample size we want to choose from the parent population. And this k is termed as sampling interval. If we want to have a systematic sample of size small n, we follow the following steps. At first, a random number is chosen between 1 and k. K means sampling interval. And it is supposed to be, say it is I. We denote this sampling random number by I. Next, we choose the first unit from the population with serial number I. And then every kth unit is selected until we have a sample of size small. The process is repeated n times, small n times, so that we have a systematic sample of small n size. Actually, this well-known probability-based sampling technique, systematic sampling, was first studied by Maddow and Maddow, and then various researchers from different areas of statistics have used this sampling technique for their own purposes. Cochrane is one of them, one of the pioneers in this field. And there are so many research material available in this topic. Here, what we have done in this paper is actually systematic sampling needs the underlying population to be finite. This is the main point that should be kept in mind. Now, we want to apply this systematic sampling in case of infinite population. Actually, in literature, we are used to see the application of systematic sampling in case of finite populations. But if we have an infinite population, how can we proceed with systematic sampling? This is our main target. How to modify the systematic sampling technique in case of infinite population. In doing so, we have approximated our infinite population by countable by a finite population. This this approximation we have suggested three approximation methods: method 1, method 2, and method 3. An underlying population in this paper has been chosen Poisson distribution. Our population follow Poisson distribution. Poisson distribution have the PMF e to the power minus lambda, lambda to the power x by factorial x is countably infinite, and lambda, the parameter of the underlying population, is greater than 0. And we all know this lambda is the population mean as well for the Poisson distribution. And the corresponding sample mean in case of systematic sample is nothing but x plus n minus 1 by 2 into k. And the corresponding in this case given by the equation I. 1. And now we come again to our approximation methods, because we have already mentioned that the underlying population should be finite to apply systematic sample. The method 1 means how will you approximate the infinite population. We just take sample of finite population. A countably infinite population defined on 0 to infinity has been approximated by a finite population defined on 0 to n minus 1. Since we need a population of capital size, population of size capital N, and our starting point is 0, so we are restricting ourselves up to n minus 1. And in that case, that's how the samples look like. If our random start is 0, then the sample consists of the units 0, k, 2k, and if our starting point is 1, if our random start is 1, then the population compromises of 1 plus k, 1 plus 2k units of the population. Here k is the sampling interval. We have already mentioned this k means capital N by small n, and so on. In that case, to calculate this, we need to calculate the corresponding probabilities. Which probability we need? We need the probability of selecting a sample having 0th unit of the population. If the 0th unit of the population comes to a sample, and what is the chance of choosing such a sample? And this has been calculated with the help of Poisson distribution. Since our parent distribution is Poisson with parameter lambda, and this is the first expression is the probability of such a sample which that contains population unit, 0th population unit, and so on. We can, in the similar fashion, we can find the probability that contains the population unit 1 and population unit 2, and finally population unit k minus 1. These probabilities all are for our approximate technique 1. Now we suggest another approximation technique, and this is method 2. A countably infinite population defined on 0 to infinity has been approximated by a finite population defined on 0 to n minus 1 after pooling population units greater than n minus n. That means the units serial numbered bearing serial number n minus 2, n minus beyond n minus 1 are clubbed, such that we get a finite population. So In that case, the sample composition should be like this. If 0 is our first unit of the sample, then it is 0k, 2k, and minus 1 into k. If the first unit is 1, it is 1, 1 plus k, 1 plus 2k, and so on. In calculating the corresponding probability of input, okay. Now we have calculated these probabilities for our method 2, and next we have applied another method of approximation, that is our method 3. That in that case we have truncated the Poisson distribution, and we have used a truncated Poisson distribution PMF, and in the similar fashion we have calculated our probabilities that are needed for the risk calculation. Next we have calculated our risk. Since the algebraic treatment is too tough, we have opted for simulation study. This is for different sample size n, 10, 20, 30, and sampling interval 3, 4, 5, we have calculated risks using our simulation study. These are the results we have obtained using R programming. This is different table for different risk calculation, and our graphs have been come out to be like this. These all have been all I have done in the using R programming language and our conclusion. Out of 3 approximating technique, the first one has been the most the best one. The first one is the best one, since in our calculation, in our simulation study, we have seen that the first method is the lowest risk. And so this is our conclusion, that out of how can we apply a finite sampling technique like systematic sampling in case of infinite population governed by like a Poisson distribution. And in that case, we have suggested 3 different approximation techniques that approximating a finite population, replacing a infinite population by a finite population. And we have studied the risks. We have compared their performance under different the sample size and sampling interval, and finally it has been observed that the first technique is the best one. Thank you very much.
Thank you so much for this presentation. Now we would like to proceed to the next presenter. So I would like to hear unmute again. I will try to unmute Dr. C. Binotini Madam for her presentation. You can unmute from your side, ma'am. I would like to request Dr. C. Binotini Madam to kindly check your audio once.
Can you hear my voice, ma'am?
Yeah, you are audible and you can start your presentation.
Okay, ma'am. Okay, ma'am. Thank you, ma'am.